Another reason is that we just learned complexing, and you see that some of these things can be put in the using complexing as well. And well, even Fourier series, it turns out that using complex expansion is much easier to do to work out than the sine and cosine, because obviously the sine and cosine are two functions. They relate to each other, but to work on that is slightly more complicated than exponential function. We actually take that approach. So we can write down the Fourier series first. So the idea is you have a function f(x), which is defined over a certain finite domain. Say you define for x is below to some, like, I mean, 0 to L. Doesn't matter. Later, we might actually choose to do 2L for convenience, but for this discussion, you just say that you have a function that over a certain domain of x, you define a function, whatever that certain function, right? And it doesn't have to be periodic, so you don't care about what outside, what the value of the function outside. You just have a function that defines over a finite domain, and you want to represent this function with sine and cosine over this domain. So the difference between Fourier series and Fourier transform: Fourier series is defined by a finite domain, and Fourier transform is you consider the domain goes through infinity, so you have an infinite range of value. That's when you do Fourier transform. Fourier series is over a finite domain, and because you wanted to explain it to sine and cosine, and the reason for doing that is sine and cosine are elementary function, and they have nice property that you can do a lot of things in quite relatively simple, like differentiation, integration using sine and cosine, much easier to do. And sometimes the function is too complicated, and you do expansion in sine and cosine allow you to analysis. Although the price you pay is that usually is infinite series, but we know how to sum series, at least as long as the series is convergent, and we know how to sum it. And so we just do it term by term and do other things, right? And that's the reason. And that originally when this is proposed, is actually a pretty great breakthrough in mathematics, because now you have a tool to do a lot of things easier, right? And so after you expand the function over this region using sine and cosine, obviously sine and cosine are periodic function. So effectively, you are saying that you are extending this function and treat it as if it is a periodic function. Although you in practice you don't care what outside, you just care what is inside this over this domain. But mathematically, it's just effectively you just copy the function over when x is greater than L, so you just basically copy the function from L into L. Copy this exact function here, and then like write in other lines from minus L to L. You just basically have the same function, just basically define x plus minus L equals, right? I should say, I mean, not x plus L, I should say. Right? Because minus L, no. Actually minus L also, that's fine, yeah. So define like that, and that's the periodic condition, okay? And so that's the idea. Once you treat it like that, then just write down the general form of the expansion, which is nothing but assumption now for now, because this coefficient you still need to calculate. So over this region, or once you treat it like a periodic function, you can say x is I use a bunch of sine and cosine to represent it. So we have a constant term, which is a0 over 2. And this 2 is just treated as for convenience. And then you sum over n from 1 to infinity. And there's a cosine term. And now for the first part, for the first formula, you treated this L equals to 2 pi. So you should just treat it like 2 pi. So make it explicit periodic. But we can write like a general period, say 0 to L or 0 to 2L by just scale your independent variable. Right? Just do a scaling. And you can still use this formula, or you can write down the explicit formula for a period 0 to L or 0 to 2L. Right? That is not difficult. In this case, because the period is 2 pi, so it's explicitly this is cosine nx. And you have the sine term. Okay, so all these terms are periodic over satisfying this condition now L is 2 pi. Right? Because those n's are integer. So that you see that right there. Both sine and cosine are periodic with a period of 2 pi. So when you write an expansion like that, the whole thing is periodic in 2 pi, right? And now this is just an assumption. You can say you assume that you can do that, right? You still need to solve for this coefficient. As it turns out, the way to calculate the coefficient is pretty straightforward. And to prove that actually is not difficult, just write it down like in the textbook. Right. This n is the same as this one. Right. And for the first one, n is all positive integer plus 0. The second one is just positive integer because there's no 0 term. The sign have no 0 term because you put 0 here, it's just 0, so that doesn't make any sense. Okay. And this includes 0. It means that the cosine 0 is 1. That's basically this is just integrate the function and divided by pi, and that will give you a sub 0. So that is this term, the constant term, but you divide it by 2 in your expansion. And this is for convenience, so that all this a sub n can use a single formula. But sometimes people write it like the whole thing as a sub 0. Then the formula for the n equals 0 term and the other n terms are different. You write down a sub 0. If this is treated as a sub 0, you write a sub 0 as 2 terms of this, right? Okay. And now that a sub 0, a sub 0 is this one, I should say. If this is treated as whole as a sub 0, then this a sub 0 is like this a sub 0 divided by 2. So you have a 1 over 2 pi. So, right? So this is the formula for the calculating the coefficient will be different from the NCO term. If you do it like that, but the text will take the convention of treating write the coefficient like that. Okay, that might be a little convenient. Okay, and to see or to prove that this is correct is quite elementary. You can just substitute this series to here, and then do the integration and convince yourself that you get the, so whatever the series multi, this integration will only pick up the a sub n term, and a sub n will be equals to a sub n. And likewise, just put in here, you pick up only the b sub n term. I mean, that doing this way will require you to realize, to calculate terms like cosine ns, times cosine ms, and n are different integer, and also cosine ns and sine ms, right? Doing all these combination of integration and convince yourself that everything is zero except when you put exactly the same n. So it's just cosine ns square. Only cosine ns square will give you the finite value. Likewise, this term will only the sine square ns will give you the finite value. All the other will be zero. You can convince yourself this way, but it's what time is you need to remind me. Okay, I still have 4 minutes. Right. We'll probably won't be able to finish this, but let's just preview it a little bit. So instead of writing it as sine and cosine, another way to do it, which is much easier mathematically, is to use the complex function, because we already learned that the Euler relation, sine is exponential function with imaginary argument. Right, so instead of doing this expansion, you can write it another way to write the Fourier series is to use a complex function. Now n we choose minus infinity to infinity, and now the coefficient is c sub n and e to the y, and instead of cosine sine, because we already know that this is cosine nx plus I sine nx, right? Right, so it already cover both cosine and sine using just exponential function. And this will be your expansion, Fourier series expansion. So at least, even at this level, this is simpler than this one. And now you can figure out the coefficient. Let's see what time. It's very simple. You uh, want to substitute this in the expansion. So let's just consider this integration 0 to 2 pi fx, choosing your notation of your f sub n, the e to the I m s, yes, right? And the idea is just put this to here. This is equals the sum of n minus infinity to infinity, c sub n equals 0 to 2 pi e to the I n plus n plus e, right? And what is this? You know how to do this in the now we bring all the complex variables in. What would this integral be? 0 except the non-zero. Yeah, when this add up to 0. When this add up to 0, this is 1. You integrate 0 to 2 pi, and it will be 2 pi, right? And all other finite term with finite integer here will be 0, because this is a periodic function. You integrate over one period, will totally cancel. So this will be our time. This is the conical delta n minus m. Okay, and that will pick you the c minus m. Okay, so c minus m, the coefficient c minus m is given by this formula, or you can now change minus m to n, to cn will be this formula. Oh yeah, I forgot the 2 pi. When this happens, you have a 2 pi. So that's minus r n, because this is the formula. Okay, so right away you can see how you get this formula. And it's much easier than what we should do for dividing these two formulas. And we will have to actually get the relationship between A sub n and B sub n and all that next time. And last time, I think we end up saying that it's easier to get the inverse from the formula for the coefficient using the complex Fourier series. I think we actually divide that, which is simple, very straightforward. I mean, using the complex series. Yes. Any function you are defined as in a certain domain, and in our case, we choose it a periodic a period of 2 pi. So you can say 0 to 2 pi or minus pi to pi, doesn't matter. So, and I mean, the real domain of your function may different from 2 pi. What you need to do is just renormalize it to 2 pi. That should be straightforward. I mean, you can actually write down the explicit formula for that, but later I will probably do that. But if you define as a 2 pi, 2 pi period, then the complex expansion is simple. Right. So that is 19.4. Right. And then we divide that C sub n. Just basically integrate the f6 e to the minus I dx over the periods of 0 to 2 pi, and then divided by a normalization. That because you substitute this into that, only the term that is the same. So we'll give you 2 pi. So you need to divide it by 2 pi. Right. That's the formula. Right. Last time we just proved by substitute this into that and do the integral. Right. And now there's several things we can talk about. The first thing you can say, you found the relationship between the coefficient of a complex series and the original sine and cosine series by just direct comparison. And you use the original series here, AC over 2, let's see, 1 to infinity. And you have the cosine. Right. Here's the cosine and sine. Then, and now you can compare. Now you can do the comparison. And to do that, you can either use the Euler relation, changes the cosine and cosine, or change it to exponential function. Either way, you can get the same thing. And why don't we use? Let's see what I think your text will use the first way, change to the sine and cosine. But one thing first is that the summation, this is from negative infinity to infinity. This is just 1 to infinity. So we can start from here and separate into 2 parts. One is I say, because the CO1 is single out. So you single out this, you have a C sub 0, and e to the I0, which is just 1. So you have a C sub 0 here. And then you have sum over 1 to infinity. Just copy that. And then you have a summation from minus infinity to minus 1. And C sub n. Let's separate into 2 series. But then we do the trick that we can always change the summation variables. So you call n, nu minus n, change the n to minus n, right? Then obviously this change to minus x squared minus I n x. This is c to the c sub I minus n, and the summation becomes the same as this one. So, okay, so that's not bad, right? And then both are the same as this one. So write it one more line. And that's n to the x. That's c to the minus c sub minus n minus. Okay, and now we're getting close. And the next step is just use the Euler relation. So it changes the cosine and sine, both of them. So for the cosine one, we have there's a cosine term here, is you add the coefficient Cn, C minus n, cosine n, right? And the sine term, we have a sine term here. The sine term here is as a negative sign because exponential minus I n, so cosine nx plus I sine minus I sine nx because of the minus sign, right? And so we have I. Both sides have the I because you have I sine. Right? I times Cn minus n. Right? Now you can directly compare this that. Or maybe the text way is not doing that. But anyway, now you can solve it. We inverse that quite easily. So this plus that equals to a sub n. And then I times Cn minus c minus n. And then the extra term is b. C sub 0 is a. C sub 0 is a sub 0 over 2. Okay. And like I said, you can inverse that and solve for Cn because if you multiply my minus I here, minus I, you get this becomes Cn minus C minus n. And then you add the 2 and divided by 2, you get C sub n. So inverse that is Cn equals to half of a sub n multiplied by minus I. So minus I sub n. Why? I want to solve for C sub n, right? This becomes C sub n if I multiply by minus I both sides. Minus I and minus I. And I add the 2. Then I divide it by 2. That's it. And then C minus n is the same, except that now I subtract. So subtract should be 1/2 n plus. But see if the text the same as the, yeah, this is what the text will get. Right? These two formula 19.5. Okay. So that's fine. Right? This is just to show that the two kind of Fourier series they are equivalent. So either using compact expansion or the sine and cosine expansion, the coefficient has you can convert one set of coefficient to the other set, or vice versa. Okay, but we can then now you can use this relationship to find a formula how you solve a sub n and b sub n, because last time we just wrote it down and we haven't actually showed that. last time I said that to show it, it's the same way, but it involves the product of sine and cosine square, sine square, that kind of thing. It's slightly more complicated, but it's not too difficult. But now we can do it the other way. Just use this formula and use the relationship between a sub n and c sub n, all that, and use this formula. Like here, a sub n is equals to c sub n plus c minus n. So just substitute this into this, and then change n to minus n, going to here, right? And so you have both terms as 1/2 pi. And by the way, I change this to x. I keep it x. I mean, your text will change x to s in the integral. It doesn't matter because x in the integral is just a dummy variable. So whatever you call it doesn't matter, right? Just keep x. And so we have e to the I n x, e to the minus I n x. And the other I change to minus n, becomes e to the I n. So you have I n. Right. And now you identify this divided by 2 is your cosine. Cosine. Right. So that's the formula for the cosine coefficient. And obviously, a0 you need to consider separately because a sub 0, and this is by comparison, a sub 0 is 2c sub 0. So 2c sub 0 is just integrating of fx over 2 pi, which is right. C sub 0 is a sub 0 is 2 times that you cancel 2, so it's 1/pi integrated fx. So you can use exactly the same formula, set the n equals 0, that will give you a sub 0. So this formula is good for n 0 because we choose to write the 0 order the constant a sub 0 over 2 that allow us to use the same formula. Okay. All right. So that's the formula for all the a coefficient. Now the b, and just use this one. B sub n is I times. Oh, that's the same consideration except that you have I here. And c sub n is e to the minus x, and then you minus c to the minus n is e to the I n. Now you can identify that should be this divided by 2 and multiplied by I should be your sign, because sign is defined this minus that divided by 2i. You can change I to the denominator, introduce a negative sign to flip the order of that, and that becomes sign. So this is the time. Right, so that's the formula. Right, and now the n is from 1 infinity. Right, so that's not too bad. Right, so you can use this formula and then these two relations to divide the formula, how you calculate all the a sub n. A sub n this way. I mean, likewise, you can use the same way you divide c sub n, and say once you have the Fourier series in this form, you can substitute this into here or there, and then convince yourself that, say, like when you substitute this into here, only the same n will contribute, will be non-zero. Say if you have cosine mx, some cosine nx, if m is not equal to n, that will be 0. So you can convince yourself that using those trigonometric product rule of cosine and cosine. And likewise, if you have sine put into here, sine all the sine and cosine product integrate over the, I get it all wrong. This is not minus pi to pi, 0 to 2 pi, sorry. Sometimes it's just writing it too fast. 0 to 2 pi. So, this way. When you see, I make an error, so the point me. Right, so because it's all defined over one period, right? So, right, so then you convince yourself that substitute this into here. The only term that survives is n, this term, cosine nx squared, and cosine nx squared integrate over 0 to 2 pi will give you 1/2 times the period, which is pi. That cancel with the pi, you end up with convince yourself that a sub n is recovered by this kind of integration, including the zero term, like the zero is going to here, which is a constant term. Then everything will be zero except n equals zero. Okay, so and likewise here, the same way, substitute this into here. The only term that survives is sine nx squared, and that will give you okay, 1/2 times the period with pi over 2 and cancel with the pi. Right? No, 2 pi over 2 pi, cancel with the pi, and then recover the b sub n. Okay, so you can do it either way. All right.